Good afternoon, professors, teachers, and fellow students. Today, I'm glad to give a presentation on our project, Speedy Tunnel. We are from Shatin Secondary School, and our school team number is 51076. First of all, I would like to give a brief description of the problem, the Brachistochrone problem. It is stated as finding a curve to minimize the traveling time of a point mass in a gravitational field. In mathematical language, we first express the traveling time in a functional, and then we try to find a function to minimize it. Let me tell you why we choose this problem as our research topic. Our idea came from a comic which is called Dragon Ball, of which the protagonist is called Tsin. He has a skilled teleportation, allowing him to travel from one place to another within a short time. Therefore, to achieve this, we think that constructing a tunnel is one of the possible methods. Our approach to tackle this problem is the method of calculus of variations. Here is the brief history of this powerful mathematical tool. In 1685, Newton investigated the motion of bodies in some liquids and used the method of calculus of variations to solve the problem for the first time. An equation of the utmost importance in this method is the Euler-Lagrange equation. The statement goes like this. If a function y minimizes the given functional, then it must satisfy the following equation, which is precisely the Euler-Lagrange equation. The proof of the equation involves integration by parts and the following lemma. For a continuous function g, if this integral is equal to 0 for any infinitely differentiable function eta, then g must be constantly equal to 0. The result is best seen by setting eta to g. In some cases, we can use a simpler form to evaluate the minimizer y. For a given functional I, if x does not appear explicitly in f, then y must satisfy the following equation, which is known as the Beltrami equation. To prove the equation, we consider the derivative of the left-hand side, which can be shown to be equal to 0 when round f over round x is 0. To simplify our work, we divide our models into two groups, one for those using rectangular coordinates and the other using polar coordinates. We start by formulating general equations for each of the two cases. Here are some notations. The traveling time t can be expressed in a functional. A differential equation is obtained by the use of Beltrami equation. Here is the general equation after simplification. For polar coordinates, we stick to the same notations. Again, we express the traveling time in a functional, and subsequently apply the Beltrami equation, and the general equation is obtained after simplification. Our first model is the original Brachistochrone problem, in which the point mass is subjected to constant gravity. Py is equal to y in this case. By our general equation, a differential equation is obtained, of which the solution is a cycloid. The next model concerns with the point mass inside the Earth, instead of the Earth's surface where the gravity is constant. In this case, we can use polar coordinates for the sake of convenience, because there is radial symmetry. Note that the solution curve lies on the greatest vertical cross-section of the Earth. By gravitational law, PR equals to negative r squared. Using the general equation for polar coordinates, we arrive at another differential equation, of which the solution is a hypercycloid. It's known that artificial gravity can be generated by rotation of an object, such as a space station. Therefore, our next three models concerns with rotating objects of different shapes. In the first case, a rectangular plate rotates along one of its edges. By considering the centripetal force, we can see that Py equals to y squared. By the same methods we used previously, we found that the solution curve is an arc of a circle. Another interesting case is when the point mass moves along the surface of a cone. To proceed, we first need to express an infinitesimal element of the arc length in terms of r. Let's look at the diagram. Alpha is the angle between the slant height and vertical height of the cone. The equation for evaluating ds can be found by considering the small triangle here. Then, as usual, we first express the traveling time t in a functional. After applying the Bertrand equation and solving, we discovered that the solution is an elliptic integral. Similar method can be applied on a rotating hemisphere. For simplicity, we set the radius to be unit length. An infinitesimal element of the arc length ds is found in the same way. We got another functional here for traveling time t. And then we applied the Bertrand equation and discovered that the solution is again an elliptic integral. After deriving the solutions of different models, we are able to generalize the solution when py is equal to y to the power n in rectangular coordinates. By our general equation, we have the following differential equation, which is separable after simple substitution. The solution we obtained agrees with our result for y equals to 1 and y equals to 2. And the integral for evaluating x is elliptic in higher degree. To sum up, for the original brachistochrone problem, the solution curve is a cycloid. And inside the Earth, the solution curve becomes a hypocycloid. And if the point mass moves along rotating rectangular plates, then the curve which minimizes traveling time is a circular arc. For rotating cone and hemisphere, the solutions are elliptic integral. I believe that our research will have some future applications. Since the world population is booming, we can foresee that living outside the Earth does have some possibilities. By varying the artificial gravitational field, one can minimize the traveling time by finding the solution curve using the method we have demonstrated. And this may serve great purpose in the future life. And then we also know that the calculus of variations is a powerful tool in mathematics. So besides the brachistochrone problem, we can try to apply it on some other classical problems, such as the isoperimetric problems or the minimal surface problem. And so that's all for our presentation. Thank you.